everyone. This is Omar Yehia, the head of investments at Mata Labs, and today we'll be talking about the economic considerations of modular roll-up services. Now, normally I'd begin by trying to define what a roll-up is, but given what we've seen on Twitter recently, it turns out it's a little bit more difficult than what it seems at face value. Now, all one has to remember is that a roll-up tries to move parts of the execution from the base layer, from the L1, off-chain, while saying something about the guarantees of the data availability. And then it ultimately ends up posting a smaller version of the data that is required to reconstruct the state, or at least say something about the validity of the state back to the L1. So the raison d'etre of a rollup really is to guarantee the correctness of off-chain execution, as well as say something about the data availability behind that execution.
And a few other things to remember. The roll-up nodes actually depend on the host chain in order to be able to update their state, because the host chain defines the state transition function, and as a place to nominally store their history, the history of the actual rollup. We know that the actual layer 1, its consensus, and therefore its security, does not in any way rely on the rollup, because it's not waiting on a block by block basis to determine what happens on the rollup. Instead, every once in a while, the rollup will post its state, which has to be consistent with the rules defined by the L1. And the bridge between them, if you were to use the word bridge, is the ability for the layer 1 to check the validity of the state transitions that are proposed by the L2 every once in a while. Now, usually people talk about this idea that the rollup, in a sense, partitions the host chain's consensus, or really its state, by allowing it to apply a subset of rules that only really apply on the rollup, so long as they are globally consistent with the rules that are prescribed by the L1. Now, because the rollup needs to know about its own state as well as the state of the L1 at all times, then the cost of running a rollup is strictly higher than running just an L1, because you're basically now having to take care of two different chains. So this must mean that there must be some utility that's generated by using a rollup that justifies spinning it up. Now, this might seem obvious, but since we're going to talk about the economics of rollups, I think it's important to highlight. Now, something to remember is that blockchains, by design, are extremely computationally intensive. It costs approximately 10 million times more to do a calculation per byte on Ethereum than it does on AWS. That is the cost of achieving the properties that are promised by a distributed ledger. And this is really the sole motivator of considering roll-up economics, because a minor improvement in the execution environment can reduce the costs dramatically. And you can see that this gap is enormous. And so there is sort of a lot of margin to be gained by trying to cheapen the execution environment while preserving censorship resistance, decentralization, and so on. Now, the basic idea is that instead of submitting transactions, or a series of transactions on the L1 and incurring the sort of base layer cost, you move this process off-chain, and there's a set of actors that are responsible for essentially doing this, and then posting the results back on chain. Now, depending on the type of layer 2, whether it's sort of an optimistic design or a pessimistic design. Pessimistic here refers to validity proofs, of course. these operators behave in slightly different ways and use very different technological architectures, but the basic principle is sort of the same. And as economic agents, they have to think about the following question: how do I provide these services while pricing them in such a way that it is still profitable for me to do so, and while the user experience is at least as good as what they would experience if they were executing directly on the L1. Now, there is this concept of application specific blockchains, which I refer to more generally as specialized execution chains, whether rollups or not, um, while using validity proofs or fraud proofs or whatever type of mechanism, they handle the execution in a modular way. And this modularity relies on a simple principle that you are able to share the security of the underlying L1, which has a cost. And perhaps there is also a way to communicate between these different layers with or without going through the base layer. Now, the utility of these modular setups lies in their ability to remove the constraints that are normally imposed on a network that's trying to bootstrap a cheaper execution environment, but also incurs fragmented liquidity, different UX, additional latency. And the premise is that these new primitives that are being built from a technological perspective allow these modular networks to build a stack that is vertically integrated and does not detract away from the user experience, and certainly offers a much cheaper execution environment. Now, when it comes to the economics of these layer twos, the name of the game here is to achieve positive network effects for unit economics without materially sacrificing decentralization and certainly not security. And what I mean by positive network effects for unit economics is that you basically escape the paradigm that you're normally constrained to on the L1, where the more transactions that you have on a monolithic L1, on average, the higher the cost of a single transaction becomes. And that's basically a statement of network demand, right? For a fixed computational supply, as the demand for computation increases, the price increases. On the L2, and that is really the fundamental insight, there is this ability to batch transactions together, and then there is this economic regime where it is possible that as the number of transactions increase across the network, you can actually have lower costs. Right? It's simply due to amortization. Right? You compress some parts of the data that's required, and you do so by allocating costs to multiple users. Now, of course, if there's only a single user of the network, this is sort of moot. But in the case that you have many, many users, each with a small subset of transactions, then you can actually have decreasing costs. Now, by definition, again, the utility of the user of the L2 has to be strictly larger than the cost of running the L2 individually and the cost of publishing data to the L1, which I really term here as the cost of inheriting the security. There's sort of no free lunch. When people say that the layer 2 in some way inherits the security of the L1, what they're really saying is that there is a cost to publishing data back to the L1 as well as the cost to actually reading the state of the L1. Yeah. Why is all this important? Well, a layer 2 economically must be designed such that the utility of using layer 2 for a particular user is strictly higher than using than the utility generated from using the L1, and the same is true for the operator. We call a layer 2 economically sustainable when the utility of both the operator of the rollup and of the user is strictly higher than operating on L2 than it is on the L1. Now here's where we get into some of the architectural trade-offs or design trade-offs associated with these different agents. So in general, we have somebody who's responsible for the data, somebody who's responsible for ordering the data, somebody who's responsible for the state of the rollup itself, and then somebody who's responsible for generating some sort of proof that's associated with the validity or the correctness of the state transition. Now, again, depending on whether we're talking about a validity rollup or an optimistic rollup, the generation of the proofs is a sort of fundamentally different process. But when it comes to sequencers, in many ways, they're sort of the same. The sequencer is the agent that is solely responsible for ordering the transactions, and then they send that sequence of transactions to someone who ultimately uses them in some capacity to update the state. And the idea behind running a sequencer from an economic perspective is straightforward. Basically, the sequencer has to design, usually algorithmically, on an order of the transactions that is strictly different than the order in which the transactions come in, that maximizes some sort of revenue. Now, of course, there might be some cases or some instances in which the ordering itself is constrained by some sort of fairness algorithm. I mean, in the case of centralized sequencers, where the user simply trusts that the sequencer will order transactions, let's say, first come, first serve basis, the sequencer is simply paid for the fact that they do this. Of course, the sequencer runs a particular set of hardware, which requires some off-chain compute costs, and they at least need to cover those costs and perhaps make a small profit on top of that. The rules by which they order the transactions highly depends on the environment and also the actual designation of the agent as a sequencer. So in the case where you have a single sequencer, it's sort of trivial. This person is guaranteed, or this operator is guaranteed to be sequencing their transactions, and so their economics are sort of straightforward. Whereas there are cases in which the sequencer is decentralized, so that you have multiple agents that can perhaps bid or can be randomly selected to generate the canonical ordering of transactions. And it is in that case that the economics start to become non-trivial. First, because you now have to ask multiple agents to participate, knowing that only some of them might be able to propose the sequence of transactions. And so if that's the case, then there also has to be some sort of profit sharing scheme amongst them, so that the ones that are idle, or at least the ones that are not at the front of the line, are able to cover their opportunity cost, or at least their sort of hardware costs. Now, this in and of itself is an entire sort of area of research, but the thing to remember is that the sequencer, even if they were to try and be malicious, really at best they can only censor transactions, or they can slow down, or in some cases stop the operation of the rollup, but they can't insert malicious transactions, because the process to guarantee the integrity of the transaction is sort of completely separate from the sequencer function. However, what that means is that we still have to worry about censorship resistance and the liveness of the rollup. The rollup is useless if it is completely secure but doesn't do anything. And so you want to design the sequencer architecture so that it maximizes liveness, and B, it also enables multiple sequencers to come in, not only for the sake of decentralization, but actually for redundancy. And this is where the economics become very, very important. And there are different sequencer design approaches, some of which include bonding or a proof of stake type sequencer, where the sequencer guarantees some ordering of transactions, and if that guarantee is sort of not upheld by the sequencer, then they are slashed. They can also guarantee certain transaction selection criteria. They can price their own transactions. They can use a global market for determining fees or a local market for determining fees. And most importantly, as we mentioned before, they can also say something about the fairness of transaction processing. And what that means basically is that they commit ex ante to a scheme that orders the transactions, and you can go back in time and audit that and make sure that that's indeed what the sequencer has done. Now, the really interesting parts about the economics of running a sequencer is that now that you have basically separated the security of the underlying L1 from the execution environment, you now have opened up a design space of different types of economic instruments, like derivatives, that could be used to run a sequencer. A sequencer, in many ways, has to hedge against the fluctuation of their variable costs, and their variable costs are, of course, tied to the L1, and they're also tied to the transaction demand. And so you can easily see that having something like a collateralized sequencer obligation, which is an instrument that's sort of analogous to a debt obligation, but in this case, the debt is not monetary, but rather the users commit to using a particular sequencer, and their commitment has to be guaranteed somehow. And then the sequencer, in response to that, commits to some sort of soft finality and deposits collateral as a bond. And what that does is, instead of being subject to the fluctuations of the spot market, whether it's on the L1 costs or on the transaction demand costs on the L2, the sequencer has some sort of forecasting ability in terms of the demand for their services. So this becomes very interesting because you can now have a set of sequencers in a competitive market go out and issue different types of instruments that are tied to their future performance. And these instruments can be priced based on their previous performance. So in the same way that you have credit rating agencies issue different analysis and ratings for the credit worthiness of different financial institutions or companies based on their balance sheets, based on their workforce, based on their previous performance. And that enables the marginal creditor to think about the risk that they're taking by allocating capital or committing to a long-term contract or some sort of service agreement with this particular provider. You can now develop a reputational system upon which you price the future performance, or rather discount the future performance of these different operators. So that becomes quite interesting, not just from a pricing perspective, but also it makes the economic forecasting problem for the sequences themselves much more tractable. And this is particularly valuable in the case where you're using some sort of proof of stake based sequencer, where it becomes very important to know upfront what the cost of running the sequencer is going to be for a given period of time, because there is also the cost associated with hedging that exposures, particularly if the bond is not in a numeraire, but rather in a different currency, something like ETH, so that the operator can hedge their exposure to that currency as well. So now is probably a good time to talk about MEV. And what that generally refers to is the capacity to reorder transactions in such a way that the person who does the reordering, or the entity that does the reordering, benefits at the expense of another entity. And of course, from their perspective, this is a positive, and from the counterparty's perspective, that's a negative. But it's useful to make the distinction between basically the two different types of MEV. There's accretive, what I call accretive, and what I call parasitic MEV. Parasitic MEV is exactly what it sounds like, where the all of the agents external to the sequencer experience a net negative, or at least the vast majority of them. It's a net negative due to the reordering of the transactions. And accretive is sort of the opposite. Now, a good example of parasitic MEV would be something like sandwiching, right? On some sort of exchange. And a good example of accretive MEV would be something like interoperability as a service, whether it's with different types of rollups. Auction clearing is another good example. These are sort of accretive to all of the participants external to the sequencer. Now, my hypothesis there is that there is enough diversity already in rollup providers, and now I'm referring to different rollups and not even necessarily sequencers, that parasitic MEV, the operator has no choice from a social perspective but to rebate it or pass it back onto the user, because there is enough of a competition for rollup providers, let alone different sequencers, that will incentivize users to move away from the environments in which there are parasitic MEV. Now, obviously, in the case where for a single rollup you have a market for sequencers, that just becomes even simpler. In the case of accretive MEV, that's where the argument could be made that in the same way that a private company provides some value for a user, and it gets to keep a bit of that value in the form of profits, the operator or the sequencer that provides accretive MEV to the users will be allowed to keep that as part of their P&L. And that shouldn't be surprising, because something like auction clearing obviously requires running some sort of algorithm, as well as incurring hardware costs. So of course the operator should be paid for that, and the users would be happy to, so long as it's within their utility framework, to pay a little bit extra for the profit of the operator. Now, speaking of profits, we know that, as we mentioned before, a marginal improvement in the cost of execution off chain can provide a dramatic improvement in the overall cost of execution, because the cost of execution on the L1 is so high. But another thing to remember is that on the L1, the inter-machine workload variance is actually quite small. So by that I mean most validators are running similar workloads. And why that's important is that on the L2, the variance is actually quite large. And the reason for that is the same reason that we mentioned before, this idea of decoupling between the execution, its efficiency, and security. This leads to what I call a sparse market for L2 computation, in the sense that you now have a very wide spectrum and therefore economic opportunity for the operators to prove different types of transactions, different types of workloads, and sequence different types of transactions as well. So now the name of the game becomes what different optimization routes or strategies could be used to reduce the ultimate cost of running the L2, whether it's from the sequencer's perspective, whether it's from the prover's perspective, and so on and so forth. And this is where, of course, we have validity proofs that come in all different kind of flavors and forms. We have data availability solutions that change the architecture and therefore the economics of storing and querying state data, how you can become extremely efficient in terms of sampling some of that data to reduce the burden of storing the entire state, and perhaps maybe you only need to store a small subset of that state, which then leads to this interesting problem of state growth management. So L2s, while the way in which they operate is sort of fundamentally different from the L1 because of the decoupling that we discussed before, at the end of the day, the rollups themselves have a state that they need to keep track of, and the state will grow over time. It might grow slower than what you'd expect for a normal L1, but again, that sort of depends on the architecture and the operational model. But at the end of the day, they run into exactly the same state management issues as the L1 does. Basically, it becomes more difficult to sync the full history of the node because you simply have a large amount of data. So the name of the game then becomes, how do I incentivize external operators to efficiently store parts of the state and enable querying parts of the state, and how do I do so without burdening the rollup itself? Because if you need a rollup for the rollup, then we haven't really achieved very much. So instead, in your palette of resources and operations that one considers in designing a rollup, they also have to consider, how do you manage the state of the rollup so that you don't run into exactly the same problem that you would normally on the L1. And this is where the data availability problem comes into play, and ultimately the cost of verification of the validity proofs or of the fraud proofs, as well as the cost of publishing the data back to the L1, always provides a sort of ceiling for improvement, because you then rely on the L1 itself to improve in order for you to reduce those costs. So instead, you have to think about, okay, how does one improve state management on the L2 side and incentivize off-chain data availability using different types of models, volition, validium, and so on, and how that introduces coordination problems, latency problems, but also how that allows different rollup operators to bootstrap their systems from scratch. So now another topic that we touched on was how does one enhance liveness and finality on these layer 2s. And again, returning to this decoupling, we now have this interesting opportunity for different types of economic agents to come in and actually improve the liveness properties on the L2s without necessarily having to coordinate or having to participate in the day-to-day operation of the rollup. And here's what I mean by that. You can now have what I call dedicated fail-safe sequencers that are paid a small fee that is weighted towards liveness without actually processing any load day to day. They sort of behave as an insurance sequencer. And if you think about insurance contracts in general, you generally pay a premium for something that you hope that you will never use or never need to use. And that's interesting because in that model, you're basically paying for an agent to just sit there and do nothing. And so long as they can provide certain guarantees that in the event that something happens, that they're able to intervene, you're happy to pay that premium. These sequencers are basically being paid to be redundant and just sort of sit there. And the reason that's interesting is because you can pay these agents in a non-native token so that it's not tied to the security of the L1 in any way. The other interesting aspect is that we know, regardless of redundancy, regardless of decentralization, you can never guarantee 100% uptime. That is a real problem for L1s. But for L2s, you can also never really guarantee 100% uptime. But what you can do is actually make the net cost of downtime much lower when you use these sort of clever economics. So you can essentially socialize in the event of significant downtime. You can socialize the loss across a multiple set of insurance providers and that are willing to underwrite that process. Now, when it comes to finality, we know that it's ultimately determined by when the proofs are posted back to the L1, and then the last roll-up state that's considered to be valid is now sort of canonical and immutable. So the name of the game here becomes, how do I provide a market for finality? And that's simply determined by the transaction inclusion. And we know from a user's perspective that they can force inclusion in the L2 at the expense of some minimum cost. So assuming that they have no time preference, it is strictly cheaper for them to send their transaction to the sequencer. But in the case that they do have some time preference, they now have to weigh that against the cost of including the transaction themselves and the probabilistic guarantee by the sequencer that they're going to include the transaction. So in the same way that we discussed these issuance of these derivatives tying the performance of the sequencer to the native demand, we can also include a similar type of instrument that guarantees inclusion within n blocks or within a finite period, and these themselves could be priced. So not only can the sequencer guarantee or forecast something about their future costs and the transaction demand on the L2, the user can also, instead of using this very coarse gas scheme lever that they're normally used to using in mempools on Ethereum, they can now have an entire spectrum of inclusion guarantees, which gets us into the topic of transaction quality. And by transaction quality, I'm really referring to the spectrum between a pristine transaction, which is a single atomic transaction that is very cheap to execute and is included effective immediately, versus a series of complicated transactions that are expensive to perform and atomicity is not guaranteed. and most transactions, or most series of transactions as a subset, sort of lie somewhere in between. And again, you can now not only have a market for single transactions, you can also have a market for bundled transactions. And the reason you can have this is because you can now have these specialized sequencers that offer you these sort of services. You can have, in the case of multiple sequencers, where one of them specializes in DeFi-like transactions or in NFT-like, auction-like transactions, and so on. They can offer you these bundled services uh, as the most market efficient way of executing them. So you can see, just based on the discussion that we've had before, that the added benefit of having multiple sequencers is not just from a redundancy perspective, but also because it adds this new vector of customizability of transactions that on the L1 were normally handled through off-chain agreements or through something like flashbots. Um, Whereas now you can have a much more general purpose, a much more robust way of doing so. And more importantly, you can price it. And so now, in an era in which applications will start to really think about how to subsidize or even eat the entirety of the gas transactions and just incorporate them as part of their P&L in order to improve user experience, they really need to be able to price not just single transactions and their latencies and atomicity, but also they need to be able to price bundles. Atomicity, of course, is sort of trivial in the case of a single transaction, but is very, very important in complex. So now that we're talking about pricing, there is one thing that I want to highlight, which is that the network fees on layer twos fundamentally differ from those on the L1. And it's really for a very simple reason. The fundamental difference between L1 and L2 economics is that the native L1 assets command something that looks like a store of value supremacy, whereas the L2 simply does not. And the reason for that is quite simple. If you inherit the security as an L2 from the L1, you must be economically subservient. And what that means is that the security layer has to be guaranteed by an asset that is not native to the rollup. But what it does do is that it opens up the design space for off-chain data availability and other off-chain services, because now the rollup can serve as the vendor for these types of services, which brings me to perhaps the most important question. How do these L2s, if they were to issue tokens, um, how does value accrue to these tokens? And more importantly, does one even need a token for a layer 2 system? And there are sort of two schools of thought. One school of thought says that simply because security is inherited from the L1, the L2 token can at best serve as a bootstrapping mechanism for the L2 ecosystem, but it is designed fundamentally so that it becomes less useful over time. Once enough activity is aggregated onto the L2 token itself, its value will sort of decay. The other school of thought is that the layer 2 itself, because it can serve as a vendor for these modular services that we described before, that it now effectively acts as the marketplace for all of these off-chain computational services. And so that can be accretive, not just to the L2 itself, but ultimately to the L1, to the extent that it enables more economic activity on the L1 than what you would nominally get without the existence of the L2. So then here the question becomes, can a layer 2 justify the existence of a token, not just purely based on the mechanics of running the rollup, but instead, can it offer value to the L1 that wouldn't exist otherwise? And with that, I will leave you with some open questions. And again, it was an absolute pleasure to be here. If you do have any comments or questions about anything that I discussed here, as well as these open questions, obviously, please do reach out. Thanks again.